Hello. Here is the agenda for presentations in our Understanding Streams workshop. My name is Matt Matheny, and I work as a stream biologist in the Stream and Watershed Unit of the Missouri Department of Conservation. In this talk, we are going to talk about watersheds. We will look at what a watershed is and how they are formed and change. We will also look at the primary components of watersheds, which are all tied together throughout the watershed, creating a connected system. So what is a watershed? One definition is the total land area contributing runoff to a particular body of water, in this case, a stream or river. In case you haven't guessed yet, this is the Mississippi River watershed. It is the fourth largest watershed in the world and has a watershed area of 1.24 million square miles. The largest three watersheds in the world are the Amazon River at 2.2 million square miles, the Congo River at 1.4 million square miles, and the Nile River at 1.26 million square miles. Watersheds are independent of political boundaries. The Mississippi River watershed includes portions of 30 states and a small part of Canada. Watersheds come in all shapes and sizes. For example, here is the watershed of an unnamed tributary to Sulphur Creek in Iron County, Missouri. This watershed is just over 2.5 square miles and is part of the Mississippi River watershed by way of the St. Francis River, Big Creek, Crane Pond Creek, and Sulphur Creek. Stream order is another method to measure the relative size of a stream or watershed. You might have seen the tributary to Sulphur Creek in the previous slide was labeled as a third order stream. Stream order is based on the Strehler method. This figure illustrates how a stream's order is determined: first order, second order, third order, and so on. A second order stream is formed only when two first order streams converge. A third order stream is formed only when two second order streams converge, and so on. For example, here is the stream order at the mouths of several rivers. The Blackwater River here in Missouri is fifth order. The Lamine River here in Missouri is sixth order. The Current River in South Missouri is seventh order. The Missouri River is eighth order. The Mississippi 10th order, and the Amazon River is 12th order. So back to our example of this third order tributary to Sulphur Creek. Here are all the first order streams, meaning those with no other tributaries. Here are all the second order streams formed when two first order streams come together. And here you can see where it becomes a third order stream and stays that way until its confluence with Sulphur Creek. So now let's look at how watersheds are formed on the landscape of the Earth's surface. There is a constant tug of war between water's erosive capabilities and the resistance of the Earth's surface. When the erosive power is greater than the resistive forces, the result can be seen as canyons, valleys, stream channels, gullies, etc. At the same time, uplift of the land surface is also occurring in some areas, so change is constant. Channels evolve over time. The evolution of a stream network is depicted in this slide. Notice that the channels expand in an upstream direction as overland flow of water causes erosion over time. As precipitation falls over the landscape, water collects in depressions and begins moving downhill. As it moves, the water erodes sediment and transports it downstream. The stream network continues to develop through the erosion and deposition processes. Channel shape will also change as the stream system develops through time. Stream channels will deepen, widen, and develop characteristics like gravel bars. Changes occur in the stream system as the amounts of water or sediment transported through the system change. Over time, the location of more resistant material influences the topography and stream network patterns that develop. As erosion wears down the areas that are more easily eroded within the stream channel, the drainage patterns begin to form and extend upstream. The map on the left shows the areas of more resistant rock in blue and the stream network that has developed around these areas. Depending on where those areas occur, you can end up with drainage patterns as shown on the right. The one shown in the pattern on the left is a trellised, which is listed in the right figure as in the upper right pattern. The dendritic pattern, which is the upper left, is the most common drainage pattern that develops. As you can imagine, there are many factors controlling the characteristics within a watershed. These 5 characteristics are ones which have the greatest influence, and they all work together to shape the way watersheds look and act. The first is climate. This is the long-term average in temperature and precipitation. Climate provides the energy in to the watershed and directly affects the relationship with erosional and depositional processes, the energy out. The climate influences the landscape that develops, as well as affecting soil types that develop and vegetation the area can support. The second characteristic is hydrology. Hydrology is the precipitation type, timing, and variability. This greatly influences stream flow and sediment transport. It also affects how land is sculpted and changed. The third characteristic is slope and topography. The slope provides the kinetic energy for water to erode and move sediments in the watershed. The fourth characteristic is geology. As we saw earlier, the geology influences the drainage patterns that develop. Geology also influences the soil types that develop as rock is broken down through the natural process of wind, weather, plants, and animals. The last characteristic is land use. Our activities on the landscape have altered infiltration and erosion rates, the amounts and types of vegetation, as well as the drainage patterns. Over time, all this erosion and deposition creates the streams and watersheds we know today, both nationally and locally. We have now looked at what a watershed is and how watersheds form, but as you can imagine, it is a bit more complicated than that. Let's take a deeper look at how watersheds operate as a connected system. Let's look at the primary components of streams and watersheds. There are 4 primary components which interact and help shape the streams and watersheds we see today: water, energy, sediment, and vegetation. These primary components are connected, working together and in balance throughout the entire watershed. Let's take a closer look at each primary component. This is a model of the primary components called Lane's balance, proposed by an engineer, E.W. Lane. You can see the primary components on the balance. The water is in the cup on the left and can be adjusted as having more or less water affecting the balance. The gradient or slope is up on the upper left of the arm of the balance and can be adjusted steeper or flatter. The sediment is in the cup or on the balance on the right, and the quantity of sediment can be adjusted there, more or less quantity of sediment, and the size of sediment can be adjusted up on the top of the balance arm on the right, from coarse to fine. The vegetation you don't see on the balance, it is considered a part of this balance and is one of the primary components. It's considered a buffer to the system and helps moderate changes as we have good vegetation conditions. When the primary components are balanced and the watershed and streams are stable, the system is said to be in dynamic equilibrium. Streams are naturally undergoing these erosional and depositional processes. As you can see with the model, things are moving from erosion to deposition, but it is not wildly out of balance. Changes in the primary components can cause a large change in the equilibrium towards either deposition or erosion. Let's take a closer look at each primary component, then return to Lane's balance. The first component is water. The important aspects of the water component are how much water there is and how fast it is moving. These relate directly to the erosion and transport capabilities of the water. Most of the work being done and changes occurring in our streams and watersheds are occurring during the high flow events. If there are changes in our watershed that increase or decrease the amount of water, the velocity of water, or the frequency of high flow events, that will lead to change in the balance of the primary components. More water or higher velocity move the balance towards erosion. Less water or lower velocity move the balance towards deposition. The second component is energy, which comes from the stream's slope or gradient. This is a plot of the slope or gradient of a stream with the distance on the x-axis in miles from the mouth to the headwaters and the elevation on the y-axis in feet. The slope is what gives the water its energy and erosive capabilities and determines what materials can be transported and what materials are deposited. As you can imagine, higher gradients provide higher energy and increased velocities, and therefore an increased ability to erode the stream and transport sediment. Conversely, lower gradients have lower energy and decreased velocities, allowing materials to be deposited. Sediment is our third primary component. The amount and size of sediment transported in streams is dependent on the other primary components of water, energy, and vegetation. Sediments range in category by size, from fines of clay, silt, and sand to larger rock sediment of gravel, cobble, and boulder. Woody debris is also considered a part of the sediment loads in streams. The important aspect about the sediment is any changes in the amount and/or sizes of sediment that are available for a stream to transport. Changes in a watershed that result in more sediment will change the balance of the components towards deposition. Change to lower amounts will lead to erosion. If our primary components of water and energy change, This will change our sediment component. An increase in water amount and higher velocities will transport more and larger sediment, leading to erosion. A reduction in water amount and lower velocity will transport less and smaller sediment, leading to deposition. Our sediment primary component can be used to define stream stability or the balance of our primary components. A stream reach is said to be in dynamic equilibrium if, over time, the amount of sediment that leaves the reach equals the amount that has entered the reach. The final primary component is the vegetation. Vegetation is important in slowing the velocity of our water component, reducing energy, and promoting deposition of sediments. The root structures of the vegetation also help reduce erosion and stabilize sediments in place. The effectiveness of the vegetation is related to the species, age composition, and density of the vegetation. The balance of our primary components will change when changes occur in the vegetation. Reduce the amount or density of vegetation, the water will have higher velocity and the balance will shift towards erosion. Increases in the amount or density of vegetation and the water will have lower velocity and lead towards deposition. Our primary components of water, energy, sediment, and vegetation are connected and in balance, providing the stability or dynamic equilibrium in our streams and watersheds. When the streams and watersheds are stable and in dynamic equilibrium, there is a natural fluctuation from erosion to deposition. As we previously mentioned, streams are naturally undergoing these erosional and depositional processes. However, we are concerned about the rate at which these processes occur. Dynamic equilibrium means these processes are occurring at a natural rate, not an accelerated rate. Changes in the balance of our primary components can lead to accelerated change and instability. Things that can change the balance or equilibrium include getting large changes in quantity of water or stream flow, large changes in the quantity or size of sediment, a change in stream slope, or large changes in quantity or quality of vegetation. Again, notice that vegetation is not present on the model, but vegetation is considered a critical component. Vegetation acts as the buffer in the system that provides stability and helps moderate the changes that occur if vegetation condition is good. All of these watershed characteristic variables and the primary components have helped to shape the Missouri that we know today. Now let's look at the aquatic faunal regions in Missouri. Missouri has 5 aquatic faunal regions. The Big River region of the Missouri and Mississippi rivers, the Lowland region down in the Boot Heel, the Ozark region in South Missouri, and the Prairie region in the north and west central parts of Missouri. Each region is characterized by different habitats and fauna. Missouri can be referred to as the Big River State, with the Missouri River running through the state and the Mississippi River forming its eastern border. These rivers are less influenced by local or regional conditions than by the rainfall and runoff from all the land they drain, indeed which is much of the United States. These rivers have large floodplains with low gradient channels flowing through deep deposits of gravel, sand, and silt. They have continuous, strong flow and can have periods of sustained flooding. Historically, these rivers were frequently braided and offered a complex suite of habitats, including islands, side channels, backwaters, permanent oxbows, and seasonal sloughs. Vast bottomland forests and swamps once covered 2.5 million acres of the Boot Heel of Missouri. The deep soils here resulted from sediment left by the Mississippi and Ohio rivers. This broad river floodplain, called the Mississippi River Alluvial Basin, is the northernmost portion of a natural system that extends all the way to the Gulf of Mexico. Frequent flooding played a significant role in the creation and maintenance of the complex wetlands of this ecological region. Very little of this complex ecosystem remains. However, Mingo Wildlife Refuge, seen in this picture, offers some of the best examples of what this region looked like. The Ozark faunal region is composed of the streams in the southern portion of the state, with the exception of the Boot Heel and a few western counties. The gradient of Ozark streams is generally steep, which causes Ozark streams to have abundant riffles. They are also characterized by having a riffle-run-pool sequence of habitats. The stream substrate is composed of gravel, cobble, and sand, and many times with boulders in deep pools along bluffs. Many of the invertebrates we sample are adapted to live in these spaces between pieces of substrate, and often attached to the substrate. Historically, the Ozarks have been covered with dense, deciduous, and pine forests. The glaciated Prairie region is composed of the streams in North Missouri, while the Osage Prairie region is composed of the streams in parts of West and Southwest Missouri. For the purposes of this class, these two regions have been combined and simply called the Prairie Faunal region. The streams in this region have a much lower gradient. This means that they are slow-moving and have very few riffles. They also tend to be more turbid due to the surrounding soil types. They are characterized by a sequence of pool-run-pool habitats. The substrate is generally sand, silt, shelf bedrock, and shale. We have now looked at what a watershed is and how they are formed. We have talked about how watersheds operate as a connected system, with our primary components in dynamic equilibrium. We have also looked at the historic nature of our Missouri aquatic faunal regions. The next presentation will talk more in depth about the different areas within a watershed and how they function as part of a connected system. If you have any questions, please let us know. You can reach Stream Team staff by phone, email, or social media. Thank you.